Hello, everybody. My name is Lenny Zeltser. I'm the CISO at Exonius, and I'm the faculty fellow at SANS Institute. I've been analyzing malware for a long time. And for me, the challenge oftentimes involves knowing the best way to start my investigation. And so this is the topic I'd like to cover with you, how you can start analyzing malware that might be designed to pursue your Windows systems, but you will perform your analysis using Linux-based tools, which I think are designed particularly well for this kind of work. So that's what we will explore in this presentation. You come across a suspicious file. It perhaps exists on a Windows computer in your enterprise, and you're wondering, what is this file about? Is it malicious? And if it is malicious, what might be its capabilities? How could I detect it elsewhere in my enterprise environment? And how could I analyze it more deeply if I decide to do that? Well, Linux can accommodate a wide range of tools and techniques that you will find useful for analyzing all sorts of malware, including malicious Windows executables. Now, true to Linux or Unix philosophy, a lot of these tools are really good at one particular task and are not good at another type of task, which is why when you're trying to use a Unix or Linux-based toolkit, it is very helpful to know what tools are available, how will we use them, and under what circumstances will one tool work better than the other. And that's what I'd like to share with you in this session. My hope is that I will show you how to get started analyzing Windows-based malware in a Linux environment. My hope is to show you just some of the tools and techniques that will get you started learning about this kind of work in your own environment. And for my demos, for my discussion, I will use a Linux-based toolkit called Remnix that I created and continue to maintain. This is available as an open source project, and you can just go to remnix.org to download a copy of Remnix. And this way you will have hundreds of malware analysis tools pre-installed, pre-configured, and we're going to use just a few of them in this particular session. If you have not had a chance to install a copy of Remnix, know that there are several ways in which you can do it. It's available as a pre-built virtual appliance that you can run in your favorite hypervisor, such as VMware or VirtualBox. You can add Remnix to an existing Ubuntu-based compatible system. You can install Remnix in a headless cloud environment. You can even run Remnix as a Docker container. So my point is, you have these tools available to you, pre-installed, pre-configured. Get a copy of them. Listen to this session, and if you feel so inclined, try to repeat some of the steps I'm about to show you in your own environment. Now, I will show you a bunch of slides, but more importantly, I want to show you some of these tools and techniques in action. And we will do this using a real-world malware sample that perhaps a bit unimaginatively is called sample. Now, I have a copy of this sample available in my environment. It is in my environment set up as a password-protected 7-zip file, and I'm going to extract it from its captivity so that it's available to me. You will be able to get a copy of this malware sample at the end of this session, and if you decide to experiment with these tools, you will need to extract the sample yourselves in your environment, and the password for the 7-zip archive will be the word malware. So here, I extracted a copy of this malware sample. It's called sample.exe. And in case you're curious, we can use this SHA-256 hash as the digital fingerprint of this file. Now, what kind of a file is it? Its extension implies that it's a Windows executable. And one of the many tools you can use to examine the nature of the file that you're about to analyze is called TRID. TRID comes with a database of file identifiers, and it is quite good at determining a variety of file types using several different techniques. And so according to TRID, this is a Windows executable, at least to a very high degree of likelihood. And indeed, this is indeed a real-world Windows executable that we will be analyzing to some extent. My goal is to not analyze this particular malware sample, but rather to use this malware sample as an opportunity to tell you about a variety of techniques and tools to get you started doing this kind of work in your own environment. And so here are the steps that I want you to consider when you encounter a suspicious file like sample.exe. What I like to begin with is examining starting static properties of this file in my environment to assess its nature, to determine what are the chances that it's actually malicious. And if it is malicious, to understand what threat might it pose to my end users, what ways are available to me to detect the presence of this malicious program in my environment, and to understand a bit about the nature of the program and how I might analyze it further. Next, I might look at certain aspects of the code of this malicious executable, at least to try to get a general sense for its malicious capabilities, going beyond looking at purely static properties or metadata about this file. And then I like to examine how this program runs, specifically how it interacts with the network. Now, to do that final step, I will need to add a Windows system into my lab if I'm going to actually run this malware in a controlled, isolated environment and observe its network interactions. These steps are just the beginning. They form the foundation for you deciding whether to analyze this malicious program further. And if you decide to do it, what you learn through these steps that I'm going to discuss with you in this session, then you will know or formulate some ideas for how to examine them using other techniques, perhaps on a Windows-based computer, if you decide to debug this malware or otherwise examine it. But those types of steps are outside the scope of this particular session. So the approach in this session is for me to show you techniques, tools, ideas as live demos whenever possible. I have captured all of these demos in screenshot forms so that if you decide to review this session later on, you can download the slides that I'm using and go through them at your own time, at your own pace, in your own environment. And there will be some additional details in the slides that I won't have time to get into during this live session, but I designed the slides to be that takeaway that you can use for further study of this topic. So let's get going, and we will start by examining static properties of a suspicious file. Now, I'm going to use sample.exe for my examples, but this is the kind of thing that you would want to do with any suspicious Windows executable that you bring into your Linux-based lab, such as the one that I'm using in my demos. It's based on Remnix. We used already one tool to get the general sense for what kind of a file this is. That tool was TRID. Another similar tool is File. We'll use Yara rules to identify some of the riskier operations that the program might be capable of performing. And I'll show you ClamScan and SignSearch as well. So let me show this to you live. As a starting point, just use File. File. Just look at File. Let's do it like this. File sample.exe. And just like TRID, File gets a general sense for the kind of program this is. As we expected, it's a Windows executable, apparently compiled as a 32-bit program. And File also tells us that this file appears to be compressed with something called PECompact2. If you've never heard of such a thing, you would probably look it up online, and you would learn that PECompact2 is a packer that sometimes malware authors might use to conceal the nature of the original code that they're trying to conceal from malware analysts and our tools. That's something to file for later. Perhaps if you decide to debug this program on a Windows system, you might need to determine how to bypass the protection of this packer. Now, something else that I wanted to mention to you is that it is useful to begin your investigation by scanning your file using some antivirus tool. And on Remnix, I have ClamAV installed. It's a free open source based antivirus tool that focuses its detection on signatures. But you know what? I like signatures as the starting point for my investigation, because if ClamAV identifies that this is malware, now I know that I'm probably not going to be wasting my time examining it. And if ClamAV gives me the name of the malware family. That gives me a starting point for gathering additional data, perhaps using open source intelligence gathering techniques like Googling things. So ClamAV says, hey, this matches a signature of some malware called Shy Ape. And now I have something that I could examine by doing some Googling to see what is this Shy Ape thing about. Now, another tool that I thought I'd mention to you briefly is a tool called SigInSearch, which looks for patterns related to cryptographic operations or compression or encoding. And sometimes it's useful to know if you will be dealing with specific cryptographic techniques for later aspects of your malware analysis process. And in this case, SigInSearch tells us that it identifies some SSH RSA key or algorithm within this program. Again, not something that I will act upon right now, but if in the future I was planning to do some debugging of this malware, then this might give me some ideas for what to look for if I'm trying to understand how does this program use cryptography to protect itself or perhaps to encrypt end users' files. There are a lot of ways in which malware could use cryptography, and SigInSearch gives me signatures of such algorithms present within the file that I'm examining. So those are a way to gather some background static properties information about this file. Now, other tools that I wanted to share with you examine static properties of files that are specifically Windows executables, or as they're formally known, PE files. Let me show you some of these techniques, some of these tools in action. The first tool is PEFrame. PEFrame is designed to extract lots of useful details about a Windows program statically. It's not running the program. It is just looking at certain aspects of this program, including giving you the hash that represents that file, sure. But beyond this, PEFrame also scans this file for several Yara-based signatures that sometimes flag potentially malicious capabilities that maybe you want to know about. The one that's drawing my attention at the moment is a Yara plugin that was triggered here called hasOverlay. An overlay is an addition to a file that shouldn't be there. There is a way to add objects or contents to files beyond where the files should have ended. That's anomalous, and oftentimes this is where attackers try to hide certain malicious artifacts. And now I know to watch out for overlays within this particular file. Also, PEFrame tells me that it found signatures of behavior related to network HTTP-based interactions. Apparently, also this malware might have the ability to interact with files and with the registry. So those are all useful details to give me a general sense for what this program might try to do when a victim runs it on his or her system, and what I might need to look for if I perform behavioral analysis in a Windows laboratory system. There are also some risky API calls that PEFrame calls out for me. These are functions that this malware might be able to call when it runs on a Windows system to interact with its environment, such as apparently perform HTTP-based interactions with websites, and that might be used to download additional artifacts or to exfiltrate data. Here's an API call that tells me that this malware might be capable of reading files, for example. So those are the kind of details you can gather statically using PEFrame so that you start thinking about what are the capabilities of this program. Now, it's always good to have more than one tool that does the same type of thing. And so an alternative to PEFrame that I like to use is called PECheck. PECheck also, just like PEFrame, gives me some general information about the file. Some of that information, though presented differently from PEFrame, is similar to what we already saw in PEFrame, such as references to risky API calls that might tell us what this program is capable of doing when it eventually runs on a victim's computer. But what I wanted to show you specifically within PECheck here is that it gives me more details about this overlay that is added to our malware file, apparently. It gives me the hash of the PE file without the overlay. And now, if I'm doing some open source intelligence gathering, then maybe this is the file hash that I would research online using Google and various other tools to see, does anyone know anything about a file that is represented by this particular hash? which is this malware file without its overlay. Sometimes attackers add overlay to a file just to change its signature. And now we know how this file might look without its overlay. But perhaps even more usefully, PE check allows me to extract that overlay. Let me show you how to do that. PE check, here are the command line parameters. This is going to be documented in your slides in case you want to do this later on, but PE check will extract that overlay, and in my case, save it into the separate file called sample.exe.overlay. Now I can examine the overlay. For example, I might extract strings from it. I could extract Unicode strings from the overlay file, and I get this string called Citrix Secure Input Active. Now you can use that string as a starting point for your investigation. Look it up in your favorite search engine to see what does this string represent. You will see that it represents some code that is oftentimes used by Citrix. And maybe that's the way that you end up investigating this malware further. Now, this is a way to extract strings from the overlay file if you're looking at Unicode strings. What about ASCII strings included in this file? Well, let's look at those as well. If you look at ASCII strings included in this overlay file that we've just extracted using PE check, you see more information that you could use for additional open source intelligence gathering efforts. So for example, there is some information about the VeriSign certification authority. There are some details here suggesting that we might be looking at a digital certificate. Maybe that is what's in this overlay file. In fact, there's also a very specific string here, DTOP Tools Co. Limited, that seems to be the name of a company. Now you have something very specific to look up in your favorite search engine to see, are there any known malware samples associated with that particular company name or a string? And this is what I would do at this point in my analysis. In fact, I have this captured in a screenshot, and I'm scrolling past some of these slides because I've demonstrated this to you live in my environment. I don't need to go through the slides again. They're available for you to pursue later as a review of what I've shown you. But I wanted to show you that if you take some of those specific strings that you discovered using static properties analysis so far, and you plug them into Google, for example. So I plugged in the name of the malware sample that ClamAV identified. Then I took that string that I've just extracted from my overlay file, plug it into Google, and now I have some contextual information about this malware sample, some threat intelligence details perhaps. Here's a blog post that talks about Deep Panda using Sakula malware, and apparently that malware, Sakula malware, apparently was using a stolen code signing certificate that used to be assigned to this particular company. So now we're thinking maybe we're looking at malware signed by the stolen digital certificate. Maybe it is somehow related to the threat actor that CrowdStrike called Deep Panda and the malware family called Sakula. Although in this particular case, this executable, if you examined it further, you would notice that it is not actually digitally signed by this certificate, as far as I can tell. What it looks like to me is that this probably stolen digital certificate or some information about it was just attached to the file as an overlay. So maybe this is designed to mislead the investigator. Maybe this file is designed to associate itself with a particular threat actor and malware family, but maybe it's a different, perhaps unrelated form of malware. We don't have time in this session to answer these questions, but my point is that when you begin your investigation, when you're in triage mode, when you're performing static properties analysis, like what I'm walking you through right now, my goal is to get you to ask interesting questions. And sometimes you will answer these questions using Linux-based tools or using Windows-based tools or using other commercial or free utilities. My point is that early investigation, you look for little tidbits of interesting information that you discover. Then you expand your search with some open source intelligence gathering. And then you pose questions that guide you through the rest of your investigation. Further searches, for example, might allow you to take this newly discovered name of a malware family called Sakula, plug in the name Shy Ape that we discovered earlier, and start looking for any kind of relationships between the two malware families that maybe were supposed to be unrelated, but sometimes are discovered as part of the same incident. So we're continuing to look at information embedded into this suspicious, or I would say malicious file, and we're using static properties tools. And I wanted to show you a few more tools that I think will allow you to look even more deeply into this malicious program. So for example, how about extracting strings that might be stored in this malicious program, but what if they're stored in an obfuscated way? Well, attackers oftentimes conceal sensitive strings from us, and oftentimes they use rather straightforward obfuscation methods. One tool for finding commonly obfuscated string patterns is XOR search. Now, XOR search will look for strings concealed using very common techniques, like a technique that uses the XOR operator, where the attacker XORs every character of a string with a key that is only 1 byte long. XOR search can brute force all possible keys, but you need to tell it what it is you're looking for. So what I often look for is the substring HTTP, because I know that attackers often conceal URLs inside of their executables, and oftentimes a simple XOR-based algorithm is just good enough for the adversaries to hide the string from us. And so in this case, we can tell XOR search to tell us whether the string HTTP is present using this simple obfuscation technique. And look at this. It finds several mentions of HTTP. Some of them are not obfuscated and are related to the digital certificate we covered earlier. But what I wanted to draw your attention to is that apparently within 2 locations in our malicious file, XORed with key 56, we see some URLs that look like they might be malicious. Why do I think they might be malicious? Because it might be a bit hard for you to tell, but this URL reads like the domain name wellpoint.com, but actually these are numbers 1 rather than letters L. So whenever I see a domain name that's designed to look like some other domain name, I'm thinking maybe this is a malicious URL and it's something that perhaps I would need to investigate. So these are the kinds of strings that you find if you know how to look for obfuscated strings. XOR search is one of the ways in which you can do it. Another tool that is useful for this kind of work is called BRXOR.py. And what's nice about BRXOR is that you don't need to tell it what to look for. What it does is it tries all possible 1 byte long keys for the XOR algorithm, and it looks up every word that it derives in an English dictionary. If it finds that it deobfuscated a string that is present in an English dictionary, then that tells the tool that perhaps it found a proper deobfuscation key, and it shows you the full string. And so this tells us that indeed, we have the XOR key 56 being used to conceal the URLs that we just discussed, but there's also another part of the URL that XOR search did not tell us, and we also see a few other strings that are apparently obfuscated using the XOR key A. We did not know to search for these substrings, so XOR search didn't tell us about these, but now we've identified some other commands that maybe we now know to look for on potentially compromised systems. My point is that sometimes one tool will work better than another. That is why when you look at what tools are installed on Remnix, you will find that there are many tools that seem to do the same thing, but they each do it a bit differently, and it's useful to examine a given executable using several similar tools. For example, another tool that I like to use is called bbcrack. bbcrack can also deobfuscate strings that are concealed using several commonly used algorithms. Its approaches go a little bit beyond what BRXOR and XOR search can handle. It takes longer to run, but I just wanted to mention that this tool is available to you. I'm going to pause it and not allow it to complete in the interest of saving some time. And one other tool that I thought I'd mention in the context of deobfuscating strings is called FLOSS. Now, FLOSS is perhaps the most powerful string deobfuscation tool of them all, because FLOSS can even deobfuscate strings that are concealed using algorithms that we perhaps have never heard of. Because FLOSS emulates the execution of the program, and it observes functions that change contents of memory, so that if a buffer in memory did not have a string before the function was called, and after the function is called, that buffer changes to what looks like a string, that's one of the heuristics that FLOSS uses to realize that it just derived a deobfuscated string. And so look, now when I run FLOSS, it is able to decode 31 strings for me. These strings are a lot more extensive than what I recovered beforehand. I see the full command that apparently will add a run registry key, which is a form of persistence of an infected system. I see a reference to what looks like a hard-coded user agent that perhaps we could use as a network-based intrusion detection signature or a network-based indicator of compromise. So there are amazing things that you can discover about malware by looking for obfuscated strings, and now you know about several very powerful tools for doing this kind of work. And so let me summarize what we have just learned in the context of examining static properties of a suspicious program. We didn't look at code, not at all, but we did look for indicators that this is malicious, and we've identified some potential ways in which this malware might interact with its environment when it runs. So for this particular sample, you saw Windows API references that indicate that it can interact with disk, file system, and the network. You saw some deobfuscated strings that revealed URLs that you might need to investigate further, and some other risky API names that would not have been visible in clear text. The tools that I had mentioned also indicated that this file might be protected with a packer called pcompact2. And when you look at the output of pframe and pcheck, one of the details it reports to you is how high is the entropy of this file's contents. The entropy is the degree of randomness, and the higher the entropy, the more likely is it that this file is packed or compressed or protected. We saw this overlay embedded into the file that appeared to contain a potentially stolen digital certificate that is related to a threat group that we've identified by name, and it's unclear why this overlay is present. Maybe this malware is related to the threat actor, or maybe this is just an attempt to misdirect us. That's something that you would need to explore to see what is this link between our file and that threat actor and the malware families named Shy Ape and Sakula. So we've asked a bunch of questions, we've answered a bunch of questions, and more generally, beyond this particular malware sample, what have we learned? We've learned that you can examine a file statically to extract clear text and obfuscated strings, to determine hash values and find other properties that are useful as indicators of compromise, as things you can look for in systems in your environment to see if your endpoints are infected with this malware family. We also learned that you can look at API names to get a general sense for what this program might be capable of doing when it runs on a Windows system. We learned how to use these details and plug them into a search engine to perform open source intelligence gathering, to learn more about this malware sample and the context within which others have seen it in the wild. And we formed some ideas, asked some questions that will guide your further malware analysis steps. So let's keep going. Now we can look at certain aspects of the code that comprises this Windows executable. Now, if we wanted to actually run this program, then it would be most beneficial to do it on a Windows system. But what can you do on a Linux box? Well, we cannot directly run this malware on our Linux system, but what we can do is use code emulators. These are tools that are designed to pretend to run the program and look for certain ways in which it would try to interact with its environment. And the first tool that I thought I'd mention in this context is a tool called Bini. So let me show you how it looks when you run Beanie here. Now, Beanie is designed to emulate the execution of the program, and it looks specifically for activities that this program might use to interact with its environment. So it'll tell you about its attempts to interact with files and registry keys oftentimes and other programs. But in this case, that's not what it tells us. In this case, it tells us that this malware will call a Windows function getTickCount. You might need to research to see what's the big deal about getTickCount, and you would learn that getTickCount is oftentimes used to time the execution of the program. This is one of the ways in which malware can detect that it's being analyzed, that it's being debugged. Because when you debug malware, you slow it down, and that's one of the ways in which a malicious program can detect that it is running in an environment that maybe it does not want to run in. Something else that we see here is attempts to call getForegroundWindow, and something about foreground window yet again. Why would malware care to look at the foreground window on the infected system? Well, in some cases, that is also used to detect whether the system that it's infecting is actually being used by anyone. If there are no windows popping up once in a while, that indicates that the system is not being used, and sometimes that's a way to detect when malware is running in a sandbox environment. And a lot of malicious programs are designed to avoid running in a sandbox because they don't want to be analyzed. So those are the kind of details that we can gather even without actually running the program. We're just emulating its execution. And another tool that can emulate the execution of this program, it's called QLTool. And let me show you the best way to invoke it. Like this. QLTool also emulates the execution of the program, and it creates a very, very detailed log of what the program would be trying to do when it runs. I redirected that log into this file, and I'm going to press Control-C to stop running the emulator and then quickly look at the log file that it produced. And what I will see is that just like I learned earlier, this malware keeps calling getTickCount, then it waits a little bit, then checks the foreground window, another getTickCount, another getTickCount, then waits, then also checks for its foreground window. This seems to me like this is code that is running in a loop to time the execution of the program and to see if new foreground windows keep appearing. This might be an attempt to just wait and do nothing until the program confirms that it's not in a sandbox, until the program confirms that it's running in an actual environment that's worth infecting. It might choose not to continue infecting the system. It's an evasion tactic designed to avoid making it easier for us to analyze the program. And one other tool that I wanted to mention as a way of emulating the execution of the program, it's called Kappa. Now, Kappa also will pretend to run the program. But what's special about Kappa is that it comes with signatures of behaviors that will allow you to identify malicious capabilities of a program even without being an expert in Windows APIs. Some of the things that I just mentioned about evasion, about the use of getTickCount, require you to know about these API calls. Kappa provides you with an easier way to get started because it will look automatically for the risky activities, and if it finds them, it will flag them and explain to you what the program is trying to do. For example, remember I said that getTickCount could be used to time the execution of the program as an anti-debugging technique. Well, Kappa detected getTickCount and explained it to us. This is an anti-debugging technique. So now you see, even if you didn't know about getTickCount before, Kappa educated you about this, and now you know what the program might be trying to do. Also, very usefully, Kappa tells you at which address within this malicious program is it trying to call getTickCount, so that if you decide to perform code level analysis, you know where to look to detect that kind of activity and examine it more closely. Kappa also told us that apparently there's a way to detect whether the mouse cursor is moving, another anti-analysis or evasion tactic. If the mouse cursor is not moving, maybe this is not a real system and the malware will not infect it. There's also another indicator that perhaps this malware will allocate memory as a way of injecting itself into another process, or in this case, perhaps into its own process. That is an unpacking technique. And if you decide to go deeper into the analysis of this program, now you know where to look in your attempts to perhaps unpack this malicious program. So those are the indicators that Kappa gives you. And something else I wanted to mention to you, you can also run a decompiler on Remnix, but it's a decompiler called retdec that's available as a standalone Docker image. You can even run it outside of Remnix, but I thought I'd mention this decompiler briefly to you. You just run retdec decompiler pointed to my malware sample, and now it will decompile this executable. It will show me what the original source code may have looked like. And now, if you feel comfortable examining source code, now you can examine the output of this tool and understand what is the attacker actually trying to do at the source code level. I'll scroll past some of the stuff that perhaps is not very useful to you and show you that eventually you will get to code that uses the very API calls that Kappa and some other tools already told us about. So now you have even more context to analyze this malicious program. And Remnix also provides you with another useful code analysis tool called Ghidra. Ghidra is a more interactive tool that has a built-in disassembler and decompiler, and you can look at the very addresses that Kappa reported to find the code that Kappa told you about. And if you are going to be doing that kind of a deep dive, you can perform some code analysis using Ghidra on Remnix if you want. Now, so the takeaways from this section is that for this particular sample, we confirmed that there are specific anti-analysis measures that are available to this malware, which means that automated sandbox-based analysis might not be very useful against this malicious program. You might need to examine it more closely using the very techniques that we're discussing here. And more generally, you now know that you can emulate the execution of the environment, and you have you can emulate the execution of the malware to examine how it interacts with its environment, even without actually running this program on a Windows system. This gives you visibility into the malicious techniques that the malware tries to implement, and it allows you to more closely examine this program using a disassembler, a decompiler, even a debugger, if that is something that you decide to do in the future. Now, another set of tools that are available on Remnix allow you to explore network interactions of a given malicious program. And here, it's very useful to know that on Linux, on Remnix specifically, you can run services that pretend to be a web server, a DNS server, or any other kind of network resource that malware might be looking for. Now, looking at how you can do that in a lab is outside the scope of this session because I just don't have time to dig into that level of detail. But I wanted to mention that I do have this information in the slides available to you so that if you decide to go through these steps in your lab, you can infect a system with this malware sample. You can use a fake DNS server, a fake web server on Remnix, and examine how this malware will try to interact with its environment when it actually runs. Now, to wrap things up, I wanted to suggest to you a few follow-up steps. If this is interesting to you, then get a copy of Remnix, start experimenting with its tools. Definitely look at docs.remnix.org. You will find there very detailed documentation about every single tool installed on Remnix. If you want to get a copy of the malware sample that I showed you right now, I'm happy to share it with you. Email me at rsac@zeltzer.com. Tell me that you're not going to blame me if you infect yourself, because you got to be careful. This is real world malware. I'll share the sample with you as a password protected archive. You might want to see some other videos that I recorded during an earlier RSA conference, for example, that show you how to examine malware on a Windows-based system. I published a bunch of cheat sheets on this topic as well. And so those are some of the takeaways for you. My hope is that you will keep learning and use this session as a starting point for your exploration of malware analysis techniques.